Hello and welcome back. In today's lecture, we shall focus a little bit on the theoretical aspects of parallel programming. More specifically, we shall look at Amdahl's law, Gustafson-Barsis law, the Karp-Flatt metric and the iso-efficiency metric. So far in this course, you have looked at various ways of implementing parallel programs, either on shared memory machines, distributed memory machines, or GPU machines. What we will look at today is whether a particular program or an algorithm, whether if it merits parallelization, how to evaluate the performance of such a parallel program, and then to decide whether what is the principal barrier for achieving maximum efficiency and speed up. So we will be able to test whether a parallel program is scalable to multiple processors over different types of machines. So let's begin by looking at Amdahl's law a bit. Before that, what we should look at is typical time measurements of a parallel program. Now, if you look at a serial program, it spends almost all of its time on computation. But as you increase the parallel number of processors, what happens is that there has to be some inherent communication with increase in number of processors. So the program will now spend some time in doing calculations and then sometimes doing communication. What you see in this graph is the proportion of time, which is in white, which is spent on communication. And you can see that as you increase the number of processors, the amount of time that is spent on communication increases. Now, typically the operations in a parallel program, they are divided into three sections. One, the computation that must be performed sequentially, computations that can be performed in parallel, and lastly, the parallel overhead, including communication and redundant computations. To illustrate this, let us look at a very simple example. An example could be something like a bag of integers. Let's say that we have a bag of 10,000 integers and we want to compute the sum of these integers. Let us assume that we are using a human calculator and the human calculator is able to do one addition per second. So, if a single human being is used or the equivalent of a serial program, what will happen is that you would require at least 10,000 seconds to compute this sum of 10,000 integers, because a human being is capable of doing one addition per second. Now, let us assume that we get 10 very similar human beings who are now going to do this computation. So we will distribute this 10,000 numbers or integers among these 10 people. The naive assumption is that if I take 10 times the resources, I should go 10 times as fast for the same size of the problem. But that's not true. What will happen is that you will distribute the 10,000 integers to these 10 individuals. Each of them will then compute their local sum in about 1000 seconds. But then to compute the global sum, only one person will be able to do that global sum and you would need an additional 10 seconds. So that makes it a minimum of 1010 seconds. So your speed up is already less than 10. I have neglected at this point of time the time it takes to distribute 1000 numbers to each of those 10 individuals and then collect back their local sums. That effectively is the parallel overhead in communication. So now let us formalize some of these concepts. So we will talk about things in some basic units where n is the problem size, p is the number of processors, sigma n is inherently the sequential portion of the computation, the one which cannot be parallelized, and psi of n is a portion of parallelizable computations. Let us now have kappa np, which is a function of both the size of the problem and the number of processors that you would use as a parallelization overhead. It is quite obvious that if you increase p, kappa np should increase for keeping the same size of n. Now, we shall define the speed up as the sequential execution time divided by the parallel execution time, and efficiency as what is the sequential execution time divided by the parallel execution time multiplied by the total number of processors that is used. So that would give you the parallel efficiency of the program. Now, let us begin with the sequential execution time of a problem size n, t of n comma 1. Now, this is equal to sigma of n plus psi of n. Sigma of n, if you remember, is the portion which needs to be done serially and cannot be done parallelly, analogous to computing the local sum of the integers in the bag of integers problem. And psi of n is now the parallelizable section of the problem. Now, we can assume for convenience sake at this point that psi of n divides perfectly amongst p processors. In most general cases, this may not be true, but for the analysis sake, we can assume this. The parallel execution time t of n comma p is greater than or equal to sigma n plus psi of n divided by p plus kappa np. Hence, the speed up, which is a function of both the problem size and the number of processors, will now be less than or equal to, or at most be, sigma n plus psi n divided by sigma n plus psi n by p plus kappa n p. The efficiency epsilon n p is now at most sigma n plus psi n divided by p into sigma n plus psi n by p plus kappa n p. So, to illustrate this example, let us look at an image processing exercise. So, let us say that you have several pixels and you are doing some sort of mathematical operations on these pixels. It could be just taking a straight average to do something like blurring, or you could do something like edge detection, any sort of arithmetic that needs to be done with the neighbors. Now, let us say for each pixel that there are 9 neighbors, and let us say that we split this problem in a vertical sense, stripwise, so that you have to communicate information across this vertical boundary. If we need to communicate the information across this vertical boundary, the time that it will take to pass the messages is 2 ts plus tw into n. And the time that it takes to compute the local subimage is 9 tc n square by p, n square being the whole big picture and p the total number of processors that's available. Now, you can clearly see this is an almost embarrassingly parallel problem. So, the speed up, which is now a function of n and p, will now be 9 tc n square, which is the size of the serial problem, divided by, there is no sequential portion of this problem at all because this problem is embarrassingly parallel. So, you will have 9 tc n square by p, which will be done by p processors, plus what you need to communicate, which is 2 times ts plus tw multiplied by n. So, this is how we would go about computing theoretically what the speedups are. Now, let us come to Amdahl's law. For Amdahl's law, because the parallel overhead kappa np, we will neglect this. The reason being, kappa np is now sort of a function of the kind of machine that you are in as well, the kind of networking hardware that you will use. And hence, for theoretical purposes, we will neglect it for now, so that now we can get some sort of theoretical upper bounds on speed up. So, the speed up, which is a function of n comma p, will be less than or equal to sigma n plus psi of n divided by sigma n plus psi of n divided by p, where we have neglected kappa np. Now, if f is the percentage of the inherently sequential portion of the computation, i.e., that if you have 100% of computation, let's say that there is a small percentage which you cannot parallelize and the rest of it can be parallelized. This will now be denoted as sigma of n divided by sigma n plus psi n. So, the speed up will now have an upper bound of sigma n plus psi n divided by sigma n plus psi n by p. And if we put in the definition of f and if we work out the algebra, it shows out that the speed up n comma p is at the most 1 over f plus 1 minus f by p, where f is a fraction of operations in a computation that has to be done serially. And this fraction is within the limits of 0 and 1. So, what is the ultimate speed up limit that one can achieve? That is when I have infinite number of processors. So, now let us assume that p is now tending to infinity. If p tends to infinity, then this denominator where you have 1 minus f over p, that term will go to 0. So, the upper limit as p tends to infinity of speed up is 1 over f. This results in some very surprising observations. So, if we were to assume that we have a problem which is 50% parallel and 50% serial, so what is the maximum amount of speed up can one get? You will be surprised to know that if f is equal to 0.5, the asymptotic limit of speed up is just 2. Even if you throw infinite number of processors at this problem, maximally it will be able to run 2 times as fast. If your problem is 90% parallelizable and only 10% serial, this asymptotic limit rises to 10. It's a very surprising result because this is the place where most new parallel computing users make the mistake. They tend to see that they have large number of resources and tend to throw all the resources at the problem they have. But it's quite possible that after some time that you might not get the desired result. It's no use to throw, let's say, 1,000 processors or 10,000 processors which you may be having if your parallel program has inherently large sequential codes. You will not be able to get too much speed up. Let's illustrate this with a simple example. Let's say that 90% of the computation can be parallelized. So, the maximum speed up that I can achieve using 8 processors, now f is 10%. So, you have psi of np now approximately equal to 4.7. So, that means if I use 8 processors, the maximum hope I have is that I will go 4.7 times faster. But in reality, I have neglected the parallel overheads kappa and p, and hence it will be even slower than that. Here is another example. Now, let sigma n be a function of n, because as the problem size grows, so sometimes the sequential operations also grow. Let that be 18,000 plus n microseconds. And let the parallelizable component be n square by 100 microseconds. So, the question is, what is the maximum speed up that can be achievable on a problem size of 10,000? So, what is the maximum speed up now that is achievable? It is 28,000 plus 1 million divided by 28,000 plus 1 million divided by p. Now, as I said, the parallelization overhead kappa np is ignored by Amdahl's law. So, it gives us the optimistic estimate or sort of the best estimate of speed up. It also assumes to a certain extent that the problem size n is constant for various p values. So, essentially what Amdahl's law shows is that execution time decreases as the number of processors increase, but it sort of asymptotes. But typically what happens is that kappa NP also grows with the number of processors, but it has lower complexity compared to psi of n by p. Hence, for a fixed number of processors, speed up is usually an increasing function of the problem size, until that psi of np then becomes less than kappa of np. So, as n increases, speed up will keep on increasing, but beyond a certain point, you will see an asymptotic limit beyond which it will start falling. So, don't be surprised that if you take a problem and give it sufficiently large number of processors, it actually runs slower than when you provide it with fewer resources. So, this is what Amdahl's law tells you, and especially the effect of kappa NP when you put it in. Now, going to Gustafson-Barsis law, Amdahl's law assumes that the problem size is fixed and shows how increasing processors can reduce time. The other way to look at this problem is that, let's say I have larger and larger problems and which I want to solve in the same amount of time, right? So, for example, instead of predicting the population for a population size of 10,000, now I want to predict some model for a population size of 1 million. So, going from 10,000 to 1 million is going about 100 times more. So, how do I then say that am I able to give 100 times more resources and expect that I would get the result in the same amount of time? So, now let S be the fraction of time spent by a parallel program using P processors on performing inherently sequential operations. So, S is sigma n upon sigma n plus psi n by P. Here again we are neglecting the kappa NP, which is the parallel overhead. So, 1 minus S will now become the parallel section of the program, which is psi n by P upon sigma n plus psi n by P. So, if I look at the speed up, which is now called the scaled speed up, it will be now equal to, after a few algebra steps which have been detailed in the slide, that psi of np will be at the most or will be less than or equal to S plus 1 minus S multiplied by P or P plus 1 minus P by S. So, what it gives us is the maximum speed up that is possible to be achieved by a program. Again, now Gustafson-Barsis law, what it essentially tells us is the weak scaling capability of a program. One must understand the difference between weak scaling and strong scaling. A strong scaling study is done when the problem size is kept fixed and you keep increasing the number of processors, and you figure out whether you get the answers in lesser and lesser time. For a weak scaling study, what you do is you keep the problem size changing in proportion with the number of processors that you throw at it, and with the hope that you are getting the solution in the same amount of time. Again, kappa NP, which is the parallelization overhead, is ignored by Gustafson-Barsis law, and hence it might overestimate this speed up. So, what it essentially says is that this is the best achievable speed up. If S is equal to 1, then obviously there is no speed up possible at all, because inherently the entire time is taken over by sequential operations. Here is an example. Let's say you have an application which is executing on 64 processors using 5% of the total time on non-parallelizable computations. What is the scaled speed up? So, you have S is equal to 0.05, psi of np, which is less than or equal to p plus 1 minus p into S. You will get to an answer of 60.85. So, what it is saying is that the scale speed up is 60.85 if I go to a problem 64 times the original problem on a sequential machine. Lastly, both Amdahl's law and Gustafson-Barsis law ignore what is called as the parallelization overhead kappa NP. Hence, they are overestimating the achievable speed up. You have to recall that the parallel execution time T of np is sigma of n plus psi of n divided by p plus kappa of np. The sequential execution time T of n comma 1 is sigma n plus psi of n. We will now define what is the experimentally determined serial fraction E of the parallel computation. Why experimentally determined is because kappa of np is highly system dependent, and hence it has to be measured differently on each system. So, we have E of n comma p, which is sigma n plus kappa np divided by sigma n plus psi of n. So, what does the experimentally determined serial fraction E take into account? It takes into account the parallel overhead. It also detects all other sources of overheads and inefficiency which have been ignored in the Amdahl's law and Gustafson-Barsis law. This includes the process startup time, the process synchronization time. Let's say that we have an imbalanced workload because we assumed that the problem was perfectly divisible, and also the architectural overload. For example, if you're on a distributed memory machine, it's quite possible that you're using different types of interconnects. It could be something as simple as your plain old Wi-Fi router to something which is very advanced like an InfiniBand switch. On shared memory machines, you could have different architectures in which memory is being accessed at differential rates. You could have multiple CPU sockets on the same board, and you could have multiple GPUs as well. So, there is no guarantee that the experimentally determined serial fraction E for a same program is going to be the same on these different architectures. So, E might either stay constant with respect to P, meaning that the parallelization overhead is negligible, or it might increase with respect to P, meaning that the parallelization overhead now obviously starts dominating the speed up. So, given psi of n comma p using P processes, how do I determine E of np? So, we have T of n comma p is equal to T of n comma 1 multiplied by E plus T of n comma 1 multiplied by 1 minus E by P. And the speed of n comma p is T of n comma 1 divided by T of n comma p. Hence, the speed up psi n comma p is now equal to the T of n comma 1 divided by T of n comma 1 multiplied by E plus T of n comma 1 1 minus E divided by P. This is now equal to 1 over E plus 1 minus E by P. Hence, you have 1 over psi, now that is equal to E plus 1 over E by P, and the experimentally defined time E is 1 over psi, which is the speed up, minus 1 by P over 1 minus 1 by P. In this expression, the thing that is measurable is the speed up through experiments. We know the number of processors P, and hence we can now determine what the experimentally defined ratio is. So, let us look at this simple benchmark problem. So, we have taken a parallel program and we have run it on 1 through 8 processors, and we have obtained the following speed up results, where psi of np is for 2 processors 1.82. That means if I use 2 processors, I go 1.82 times faster. 3 processors, it's 2.5 times faster. 4, 3.08, so on and so forth. What I need to figure out is what is the primary reason for the parallel program in achieving a speed up of only 4.71 on 8 processors. Is it inherently the sequential nature of the program, in the sense, is there a large sequential chunk, or is it because of the parallel overhead as I keep increasing the size or the number of parallel processors? Okay, so let's see what is the primary reason over here. One thing that must be told is that whenever you're doing a speed up study, it is always a good process to follow by doing several time averages. What do I mean by that? When you run the experiment for 2 processes, it's better to average 5 times. When you run the same experiment for say n processes, always average it at least 5 times. The more the averages, the better. The reason is that these times get also affected by different operating system procedures, and in order to get a more thorough result, it is always better to do sufficient averaging. Now, let us look at the results of this analysis. So, when I compute E of NP corresponding for each of this data point, I find out that E of NP based on the speed up that I have obtained is just 0.1. Now, since the experimentally determined serial fraction E of NP is not really increasing with P, it's a constant 0.1 whether it is 2, 3, 4, 5, 6, 7 or 8 processors. What we can conclude is that the primary reason for poor speed up is that 10% of the computation is inherently sequential, and parallel overhead is not the reason for poor speed up. We can look at another benchmark problem where I do the same study with 8 processors, but with the speed up data slightly different. Now, in this case, when I determine E, you will see that E keeps increasing with the number of parallel processors. So, what we have determined over here is that the serial fraction E increases with P. That means the parallel overhead also contributes to the poor speed up, and at some point you will start seeing a significant slowdown once the parallel overhead becomes large enough. Okay, thank you.